Section 3.3 is called Exponential Functions as Mathematical Models. And what that means is we'll be seeing how exponential functions are used to describe quantities in the real world. We're going to start with something called exponential growth. And this is a model that describes both compound interest and population growth. By exponential growth, we mean we're talking about the function q of t equals q sub 0 e to the kt, where k is a positive number, a number greater than 0. Q sub 0 is the initial or starting quantity. So initial means starting, beginning. And to see why that is, let's put in the starting point, t equals 0. T equals 0 is the start time. So if we plug that into this model, we have q sub 0 e to the k times 0. In other words, q to the 0 e to the 0. Q sub 0 e to the 0. Now, what is anything to the 0 power? Yes, it's 1. So by plugging in a 0 for the time, we end up with that number, that constant that's sitting out in front of the exponential. And so that's why we call it the starting quantity, and we denote it q sub 0 to give it the flavor of being something at time 0. So in other words, q sub 0 is the same thing as q of 0. By the way, this q sub 0 is also known as q naught. Naught is an old-fashioned word for 0, and it's what I'm used to calling it, so you'll probably hear me sometimes say q naught instead of q sub 0. So I wanted you to know what that means. Anyway, the other constant in this function is k. K is called the growth constant. And the reason it's called that is the rate of growth of the quantity q is proportional to q itself. In other words, the rate of growth of q is equal to some number times q itself. So this, I'm not saying here q equals kq. That's not what I'm saying. I'm saying the whole rate of growth of q is proportional to q. Now, in this class, we won't be able to see why that translates into this equation, but it does, and so that's why k is called the growth constant, because it's the constant of proportionality between the rate of growth and the size of the quantity itself. Again, we won't be able to see why that's the case in this class. Let's see an example. There are 10,000 bacteria initially present in a bacteria culture and 60,000 bacteria after 2 hours. Assume the bacteria population is growing exponentially. Find a function giving the number of bacteria present after t hours, and then how many bacteria are there after 4 hours. Where you want to start with a problem like this is as soon as you see the words growing exponentially, that tells you that we're dealing with a function of the form Q of t, quantity at time t, is the initial quantity, Q sub 0, times e to the kt. Okay, so growing exponentially means this. Now, then it says find a function giving the number of bacteria present after t hours. Well, don't we have that? We do sort of, except that there's constants we haven't filled in. So this is a very general exponential growth model, and it doesn't tell us in this particular situation how to answer questions. So the question here is, the last question, how many bacteria are there after 4 hours? See, we can't answer that yet, because even if I plug the 4 in for time, I can't do this on a calculator because I need numbers for Q sub 0 and K. So how are we going to get that? Well, let's look at the other information we were given. So we were told there are 10,000 bacteria initially present. Hey, that's our initial quantity. That's saying Q sub 0 is 10,000. So 10,000 bacteria initially present goes along with Q sub 0 equals 10,000. Knowing that Q sub 0 is 10,000, that means we have a more specific exponential growth model. We know that our quantity at time t is going to be 10,000 times e to the kt. But we still, in order to answer questions with a calculator, we still need to know what k is, and that's why we have this other information. So that other information said quantity after 2 hours is 60,000. So that 60,000 after 2 hours goes along with this statement, Q of 2 equals 60,000. Now, what does that tell us? Well, it tells us that if I plug a 2 in for t into our model, what I get is 60,000. Right, this is Q of 2. It's just the formula for Q with a 2 plugged in. Now I can solve this for K. Let me rewrite this. 10,000 e to the 2k equals 60,000. And we saw in the last section how to solve exponential equations like this. We first need to isolate the exponential expression by dividing, in this case, by 10,000. Now I take natural logs on both sides. So ln of e to the 2k will equal ln of 6. And remember, the whole point of doing that is that the ln and the e cancel each other out, leaving me 2k equals the ln of 6. In other words, k equals 1/2 times the ln of 6, dividing out the 2. Or you might think of that as ln of 6 divided by 2. Just remember that that is not equal to ln of 3. You can't divide the 6 by the 2. You're dividing the whole ln by 2. So at this point, we have a very specific formula or function for this particular bacteria population. Quantity at time t will be 10,000 e to the k. K is 1/2 ln of 6, and then times t. Now we can answer questions such as, what is quantity at time t equals 4? So Q of 4 will be 10,000 e to the 1/2 ln of 6 times 4. I'm going to put the 4 in the front. Doesn't matter where you put it, but I wanted it to be clear we can cancel with the 1/2. So what we're going to enter into our calculators is 10,000 e to the 2 ln of 6, which works out to be approximately 360,000. And that is bacteria.